All right, well, looks like we've got plenty of people here, so I think I'll probably just get started now. John, you can go to the next slide. Start off with, who am I? My name is Paul Ross. I work with Compose Systems. We're a consulting company based out of the greater Boston area. We're all very passionate about well-crafted code. Can move to the next slide, John. So what am I talking about here today and why? We at Compose Systems all use object-oriented code pretty heavily. We use lots of abstraction layers. So why should you use object-oriented, and why should you maybe take some time to think about how you use your abstraction layers? Well, there are all these promises of object-oriented code, like reusability, making code that's easier to test, reducing coupling, things like that. So if you kind of ask yourself, have you ever used an API where some toolkit or module gave you some code that you thought was really useful, but the way you would like to use it didn't match the way the API was written. So your calling of that API, your application was forced to adopt to the paradigm of that API. So a quick example would be if the API was written as the actor framework. You don't like the actor framework. You don't want to deal with actors. So even though these actors do something useful, you don't really want to use them. It's one quick example of a reason that maybe you should use better abstraction layers. John, you go to the next slide. So when we talk about OOP, I think we've all kind of heard disaster stories about people who have started trying to use OOP, or they worked on a project where people were using OOP and it was horrible. They had the IDE slowed down to where it was unusable. It was overly complex. They said, someone used 50 classes to do something they could have done in 2 VIs, right? We've all heard those things. Well, the key to using a powerful tool is using it correctly. And one of the keys to using object-oriented code correctly is to create the right abstractions. John, you go to the next slide. So like I said, I'm going to be talking about abstractions. A quick side note here. I'm going to refer to abstractions as interfaces. I may use the two interchangeably. I realize that they're not interchangeable, especially in the software world. I know that we now have true interfaces in LabVIEW. When I call an abstraction an interface, I mean it as an interface or a boundary between two modules of code. So you think about if you're calling an abstract hardware driver, that abstraction is a boundary between the caller and the concrete hardware driver that you've written. That's what I mean by an interface. My actual uses of interface, because I'm assuming I'm going to get questions about how you use interfaces. My use is I've played with them for a couple of hours. In those couple of hours, LabVIEW crashed probably almost every 10 minutes. When I was trying to rearrange class hierarchies, change inheritance of interfaces, it just wasn't stable enough for me to consider using LabVIEW 2020 for real project work. Hopefully it gets there because I think they will be pretty useful. But just for the moment, know that when I call an abstraction interface, I'm not talking about LabVIEW interfaces or necessarily the true computer science term interface. I'm talking about it being a boundary between components. Yep, next slide. So what is an abstraction? I found this definition online that I liked. The key part that I liked is that very end sentence, the goal of abstracting data, and you can even ignore data. You can think of it as abstracting functions or modules. The goal is to reduce complexity by removing unnecessary information. Next slide. So if you're anything like me, I think a lot of us probably learned about abstractions in LabVIEW through hardware abstraction layers, right? This is, at least for myself, this is how I learned about OOP, is this abstract hardware device, then maybe a specific type of hardware device, then an actual specific device, build up these big inheritance hierarchies. That way, that was kind of how I learned about abstractions. It has been my experience since then that these types of hardware abstraction layers just grow and grow and grow. There are lots of unnecessary coupling. It's usually a waste of time. That's been my experience anyways. So I'm going to kind of talk about using abstractions in a bit of a different way. Next slide, John. So I'd like to kind of focus this presentation on these two use cases, or two different ways of thinking about abstractions. One of them, as I mentioned, is a boundary between modules of code. So that means just creating an abstraction to separate two pieces of code. And this could be two pieces of code that are from different sources. So maybe an external piece of code that someone else wrote in your application. You use an abstraction purely to put a line in between those two codes so that your code isn't directly calling this other code. The other way I'd like to talk about abstractions is using them as wrappers around vectors of change, and kind of concentrating on how we can use that idea to build better APIs. Next, John. You go next. So I'll start with kind of talking about abstractions as interfaces. So when we write applications, at least my applications that I tend to write, they are usually composed of code from several different sources. So most of my applications have some sort of external reuse code, which may be some publicly available toolkit. A quick example would be, the NI Modbus library, or the OpenG toolkit, something like that. Something that you didn't write, you don't have ownership over. You don't control who changes it, makes updates to it, and stuff like that. Then you may also have some internal reuse code, something that's not necessarily specific to this particular application, but maybe is specific to your company, whatever you do. Then you've got the application-specific business logic, the code that is specific to this particular application. If you have a UI, the application-specific UI, and then a framework that maybe ties it all together. And in theory, these things are all kind of neatly there, separated out from each other. That's not how it actually looks in reality, right? Next slide, John. In reality, this is closer to what it looks like. Everything is kind of mushed together in our application. Our internal reuse code may call some of that external reuse code that our main end application also calls. All of this code may be tied to the framework. The UI may call that external reuse code, and the business logic may call it. So it's all kind of mushed together. Next slide. And what's wrong with that? Anything? I would say that yes, there is something wrong with that, because you've got a lot of different vectors of change that you don't have any isolation from. So one example is that your application is dependent on all these modules that you, as someone said, don't forget about legacy code. Yep, all these things that are mushed together, and there's no boundaries between them. So when a change occurs in maybe something that you don't have ownership over, so if you depend on some external toolkit and the developer is still making changes to that toolkit, and they publish a new version, you go download it and bring it into your code base. Now everything's broken, right? Everything's broken because the developer of this toolkit doesn't care about you and your use case. They're making the toolkit for their use case, and they've made some changes that break your implementation. And now you have to fix this in 50 different places because there is no clear boundary. So if you can create a boundary between these packages and reuse code and your specific business logic, you only have to fix that in that one spot, and that one spot is that boundary. Next slide, John. So in theory, it would be nice if we could create a set of interfaces to kind of separate everything out, right? We've got our application-specific business logic, we've got our application-specific UI, we've got the application itself that kind of ties those two things together, and then we have a bunch of interfaces to all these different modules. We have an interface to the framework, an interface to our internal reuse code, to our external reuse code. Everything's happy, beautiful, we love this. Next slide. The problem is that this is not reality, right? So if our internal reuse code is complex at all, it, as I mentioned earlier, probably calls on this external reuse code. And if we were to take this idea, this theory that we should have interfaces between modules. That would mean that our internal reuse code now has an interface to the external reuse code. And maybe that external reuse code is the same external reuse code that our main application uses. So you would have two interfaces to the same code. And if your internal reuse code is complex and there's stacks and layers, which at Compose System, most of our internal reuse code is built upon layers, stacks, you would have many different sets of interfaces between these layers that really are just creating bounds between the same stuff. So it gets very complicated very quickly. Next slide. So let's kind of look at a quick, simple example to maybe think about when and where we should create these layers. So our main application depends on some sort of widget driver, which also depends on an event logger, and our main application also depends on an event logger. All right, next slide. And we think that this is probably bad. So what do? We create this abstraction for our driver, widget driver abstraction, and our main application depends on that abstraction. Our widget driver inherits from this abstraction, and we're happy, right? What's the problem with this? The problem is that when we create this abstraction, we probably created it one of two ways. One, we created the abstraction specifically for this driver, or we created the abstraction specifically for this application. If we created the abstraction specifically for this driver, that means that the main application's use of the abstraction is really still tied to the driver. And if we created the abstraction specifically for the application, that means the driver is now tied to our use case. Next slide. So what's the problem with that? The problem becomes when you want to reuse this driver. So you have your next application that you want to reuse this driver. You have to reuse the abstraction because your driver inherits from it. So your application is already going to be dependent on that driver. And let's say maybe your secondary application uses a different paradigm than your first. Your first one is, let's say, actor-based. So you made your abstraction actor-based. You got a bunch of abstract messages, but your secondary application where you want to use this is not actor-based. The person who wants to use this driver in your company doesn't want to use actor messages. They don't want to use the driver this way, so they ask you to modify it for their use case so that it can be called by their application. So what we're doing, we're forcing changes. When we change the abstraction, we're forcing changes in the driver. And these changes are being forced on this concrete driver, this real thing that maps to a real piece of hardware based on use cases that the driver should not be dependent on. So you've kind of got concrete real code being forced to be changed by something that should have absolutely no dependence on whatsoever, which is how it's being used. Next slide, John. A more obvious example that we may be more familiar with is just kind of generic hardware abstraction where we've got some sort of analog input driver. We've created analog input driver abstraction. And then over time, maybe we want to reuse that, or maybe this goes into some sort of machine that also gets a new piece of hardware that has an analog input driver that also has an output. And we want to reuse this abstraction that we already created, but we realize it doesn't quite map exactly the way we thought it would. So we modify the abstraction. We create a higher level abstraction, a hardware driver abstraction, and then we create two layers of that. And this grows and grows and gets overly complicated over time. And again, we're forcing changes in this concrete driver based on something that the concrete driver should not be dependent on. It should not be changed because we got a new piece of hardware that we wanted to add to the system. Anytime we change the abstraction of this driver, we're changing the driver. So we're forcing changes in code based on something that should have zero dependence on. This is bad. Next slide, John. So what's the solution? What's a better way to do this? First of all, when you have a piece of hardware and you want to write a driver for it, write the driver well. Write it so that you provide a clean, easy to understand API that maps to the actual functionality of whatever this thing does. If it's a multi-function DAC that has 50 different things it can do, write your driver so that it exposes all those things. Give it some real meat in terms of if there's the ability for this driver to lose a connection. So let's say you're talking to it through serial communications, you should probably have some asynchronous background behaviors that are trying to connect and reconnect in the background. As a consumer of the driver, when I call Initialize, I don't want to have to recall that if the connection is lost. I want it to do it on its own. So build this driver with the meat so that when you go to use it in another use case, all that's contained within this driver. And don't worry about creating a top-level abstraction. Just create the driver as it is. Give it a good, clean API. Next slide, John. Then, when you go to use this driver in your application, maybe this driver does 50 things, but you only really care about 2 of them. Your use case is you only need 2 of the functions that the driver exposes. So what do? You create an abstraction for your use case. So your main application needs to call 2 of these functions. You create an iWidget driver abstraction that only exposes those 2 functions. It's a super thin class. It's only got 2 methods. There's 2 functions that you want to call. And then you create a child of that, which is a wrapper around your actual driver. And in LabVIEW, this basically looks like your concrete thin widget driver wrapper has, as part of its class data, the widget driver. We have created a boundary. By doing this, we've created a boundary between our use of the driver and the driver itself, right? And our main application is not dependent directly on the driver, and the driver is completely isolated from changes in our main application or the use case. And when we go to try and use this driver on another application, we do the exact same thing. We create a very thin, very easy to create abstraction, a very thin wrapper around the driver. The code in these things is super simple. It's basically just mapping calls to the driver. Super thin, super easy. Next, John. So at the start of this, I was kind of talking about layers of reuse, and what about the event logger? So if our widget driver depends on the event logger, which I suggest that it should, if you're writing powerful drivers that do all the asynchronous behavior in the background, you probably want some injectable event logging in there to know when the connection is lost, when it's remade. Maybe you want to track the actual strings that you're getting when you send and receive messages to the physical layer, things like that. So if you follow this pattern where you create an abstraction between every module code, you're going to have an abstraction that your widget driver uses for the event logger, and then a wrapper around the event logger, right? And what's the problem with this? So if your application uses 5 different widget drivers, that means you're going to have 5 different abstractions around the event logger, in addition to maybe an additional abstraction around the event logger you have in your main application, right? So this could get very overly complex very quickly, lots of code that you maybe don't need. Next slide, John. So what's the answer? Is this all worth it? And I don't have a good answer for you. There are some guidelines that we should look at, but it's really going to kind of depend on a use case by use case basis. Next slide, John. Like I said, there isn't a one-size-fits-all answer. A few things to be mindful of. Depend in the direction of stability. So this is the stable dependencies principle. If the package that you're depending on is unstable, that means it's actively being developed. So let's say you've got a GitHub repo and you go look at it and there's commits still happening very regularly. This package is unstable. It's still being developed. There are changes in it that could affect your code. You should probably create an interface between the code and the package. Another thing to look at is the weight of the dependency in relation to the weight of the caller. If whatever you're developing is really simple and it has a dependency on some giant framework or a bunch of code, 1,000 VIs for a package that's 5 VIs, you should probably create an interface between those 2 layers. Something really simple probably shouldn't depend on something huge. You should also look at the scale of the dependency, right? Is it you're dependent on it because of one method call in one spot, or is it that you have 50 classes that all inherit from some base class in an external framework? If that's the case, changing that dependency is going to be a nightmare. If you ever need to, if you ever wanted to use a different framework, you're going to be in a tough position because that dependency is so throughout your code and so heavy that any moving away from it is going to be very difficult. And so one way you can get away from that is create an interface to this framework, create a concrete child that calls your classes and maybe calls a base class that your classes inherit from to create that layer. And this may or may not be feasible. I think the key here is to be mindful of these dependencies. Be aware of, if you're developing code and you're using some messaging framework, whatever it is, be aware of the fact that as you develop your code, it is very tightly coupled to this framework. And simply being aware of that and being mindful of the fact may kind of help you develop code where the meat of your code isn't tied to the framework. It's more there's a boundary between the two. And Ravi, I'm going to mute you. John, next. So the other type of abstraction or reason for abstractions that I'd like to talk about is vectors of change and the single responsibility principle. Next slide. So the single responsibility states that a class should only have one reason to change. There's a common misunderstanding that the single responsibility principle means the class should only do one thing. That's not true. Classes often do a lot of things. The key there is a reason to change. And if you have a class that does a lot of things and there are a lot of different reasons to change, that class should probably own a bunch of other abstractions that wrap around those reasons to change. So what I'd like to do is kind of look at SRP and vectors of change or reasons of change through the lens of how am I going to use this API and how can I write this API in a way that is makes it easier for others to reuse or to use. Next slide. So here's a really simple real world problem that I just ran into on a project. I needed to call the command line and LabVIEW's interface for calling the command line, I think we all know, is not the best. It's a blocking call. That in itself kind of makes me not want to use it. I used a lot of actor-oriented programming. I don't want an actor blocked while I'm waiting on a response for the command line. This particular use case, it could be up to a minute before I get a response back from what I'm doing. So I want to write some sort of package, some sort of interface to the command line that's a little bit better than what we get right out of the box from LabVIEW. All right, next, John.
Someone was just asking for an example for a reason to change.
An example for reason to change. So what is a reason to change? A reason to change, so I'm going to give a better example or get to an example, but in this case, a reason to change could be so we're talking about the command line. The reason I don't like the command line interface in LabVIEW, the default one, is that it forces you to adopt to its paradigm, which is a synchronous blocking call. And when I use actors, I don't want a synchronous blocking call. I want to be able to basically send a message to this thing or request the completion of this thing, and when it's done, give me my results back. And the way that I get those results back is a reason to change, right? So if I create this API for calling the command line that gives me my message back the way I want it, that's a reason to change, because you as a developer, maybe you don't like the actor framework, you don't want a message back, you want an event back. That's a reason to change. The key, kind of stepping back, the key issue that I have with the command line interface in LabVIEW is that it's not asynchronous, right? So one thing that I could do, one reason to change, would be to create a package that gives me an ability to asynchronously run a function and get the results back. And a reason to change would be, what function do you want to call? Do you want to call the system exec? Or maybe you want to read a large file, right? That's a reason to change. You want something a function to happen asynchronously, and you want to get the results back. So let's say you want to load a large file and have the contents of that file be returned to you once it's done. So here I've created this asynchronous function interface, and I've created two abstractions, a function abstraction and a function return abstraction. And what I'm doing here is kind of piggybacking off the actor framework. So this asynchronous function interface has one public use method, which is new function request. You pass in a function and a function return, and all I do is send the root actor framework actor a message to execute this function, and then stop the actor as soon as it's done. So if you guys are familiar with the actor framework, what we see here is the do method, where we've sent the actor a message, and that message is execute this function and return the data the way we want. So in this case, there are two reasons to change. The reason to change would be what function you want executed. The other reason to change would be how do you want the results of that function returned to you. Next slide, John.
All right, we have another question if we wanted to address that while it's secured. Hey, Rodrigo.
Rodrigo, how is composition being implemented in a way that avoids elements of the relationship depending on each other?
Well, I won't steal it.
I'm not sure I fully understand the question. Elements of the relationship depending on each other. I don't, if I'm understanding correctly, the elements of the relationship do depend on each other, which is often okay in a composition relationship. It's not necessarily a problem that you have a dependence on each other. Maybe I can come back to this question at the end. It's unclear.
Yeah,
or we can
have some words in there too if you want to keep going.
If the caller is interested in the results of the message. I think I will probably explain the answer to the active framework question as I kind of go on this. So my concrete implementation, I created this asynchronous function interface, and my concrete function that I want is a system exec call. And just for the purposes of this example, I created an event callback, which would return the results of the call through a user event. And you see basically just a simple example calling ping. It asynchronously does this, and when it's done, it fires off this user event. So I've created abstractions around the function call and the return. But is this really necessary? Next slide, John. In my use case, it's not necessary because what I'm doing, I'm calling the command line, but there's a significant amount of code before I call the command line to build up the command, and then there's a significant amount of code processing the response, and that is all very specific to the command line, to what I'm specifically doing. If my calling the command line was to change, everything around it would change, so there's no reason for me to abstract the direct call to the command line. What I want is a interface to the command line, and I want it to be reusable in a way that someone else could use this toolkit and have it adapt to their paradigm, however they program. So what is the vector of change there? The vector of change there is how do you, as a user of this toolkit, want to use it? And that's what I have this command line callback abstraction. So what I'm doing here is using .NET calls to start a process, call the command line. And if you go to the next slide, John, I register for some .NET event callbacks when you receive the standard output or an error or exited. They're all .NET callbacks for these events, and I pass this callback interface into those callbacks. So you as a consumer of this API can be notified the way that you want, right? If you want an actor message, sorry, I got distracted reading. If you want an actor message, you can create a wrapper of an actor message that inherits from this callback, and you get a message back to your actor when you get a callback that the command line spits some data out, or an event or error occurred, or it's complete. Or if you use, a queued message handler, you can create a child of this interface that has a reference to your queued message handler queue, and it sends you a queue or sends you a message on that queue. So again, the vector of change here for this toolkit is how is it going to be used, and you as a user inject your particular use case. How do you want the results, the output of the command line back to you? Next slide, John. So the original solution that I showed was a layer of abstraction that I didn't need in this particular use case. If I wanted to give this to someone else to reuse, say, hey, I figured out a better way to call the command line. Here's this asynchronous function interface. That's a little bit of bloat that they probably don't need. I think it's a neat idea, this asynchronous function interface, and probably could be useful in some cases. For my use case, I don't think it's useful. I directly want to call the command line. I want to provide a toolkit that allows others to directly call the command line, and the vector of change really is how do you get the results back. Next slide, John. So furthering this idea, I'd like to kind of talk a little bit about hiding actor APIs. Often we want some asynchronous work, whether you use the actor framework to do that or your own kind of homebrew actor framework, and there's a lot of them out there. You want the actor to do that asynchronous work, but often the vector of change isn't the asynchronous actor component. In that case, abstracting the actor isn't really necessary. It's often better to hide the actor inside an API and inject the vectors of change. So let's kind of look at a real world example of that. Next slide, John. So I'm working on a few projects where I need to communicate to devices over TCP IP. So I want a abstraction or an API around a TCP client server, and I want it to do all the grunt work for me. I want it to reconnect or try to connect when I initialize, and continue to try to connect until a connection is available. If the connection goes out, I want it to attempt to reconnect for me. I want it to pull for messages for me. I don't want to have my code have some loop dangling off where I'm sitting there polling, reading messages. I want to be notified that a message came back to me. I also want the actual API to be really, really simple, and I want to use library strings and variants in the messages. And I'd like the end API to reflect that. But I'd also like all the pieces that I use to build up this API to be designed such that if I wanted to use some other different messaging format, I could do that. So the end API that I end up with here is this network messenger. The main class that I use, the API you call into, has really three methods: construct client network messenger, send message, and destroy messenger. That's about as simple as you can get, right? And it does a lot of powerful stuff. Next slide, John. So how did I build this up? So let's start at the bottom, creating connection, right? I want to create a in this case, a TCP connection, and that may not immediately be available. So I want some asynchronous worker of some sort to attempt to create this connection and continue to attempt to create this connection, and then call me back when it's available. I don't want to be stuck waiting on this action. So I create an actor called the connection factory handler. I create an API because me as a user of this, I don't need to know about the fact that there's an actor running in the back. I just know that I want to request a connection and I want to get it back to me once it's done. So the API is super simple. It's got a construct factory session, a request connection, and a close session. 3 methods, that's it. What are the vectors of change here? The vectors of change are, how do I want to be notified when this connection is available, and what type of connection to create. So those are my two abstractions. Those are the two vectors of change. You as a user of this may not want an actor message back. You may not want an event back that the new connection is available. Maybe you want it thrown on a functional global. I don't know. Whatever it is, that's one vector of change. The other vector of change is what type of connection do you want created. So in my concrete use case, the two types are a TCP client and a TCP server. But by creating that abstraction, I also allow myself to test all the business logic around the asynchronous retry behavior. Next slide, John. So digging into the code, first method here is, this is the API, construct the session, which means launching an actor. Again, this actor isn't in any way exposed to the end user. I inject the concrete factory type, which defines what type of connection to use. I launch the actor. This method in the middle there that is kind of hidden, I send the actor a message to create a data value reference of the object that I send to it, and that's a message that I can send to any actor. So one thing that when I started using the actor framework, I didn't really think of, that I've kind of now started to think of, is that you can send any actor any message you want, and if you don't force a typecast in that message, it's not going to affect the actor in any way. So what I'm doing here is, because I want this API to be by reference, I want the user of this API to know that they're interacting with the reference. So the wire that comes out is a reference to this class, but I also want this reference to be safe in terms of its lifetime. So if we call this construct method and I create the reference here, this reference is tied to the lifetime of the VI hierarchy where this was created. By sending the actor a message to have it create the reference, that background worker owns the reference. So that reference is completely safe as long as that background worker is still working. Next slide, John. So when I request a connection, I send a message to the actor. Again, this is hidden from the user. The user calls into this by reference API and passes a new connection request. And this is the vector of change, what to do with this connection once it's available. You go about your business, and when that connection is available, it's passed back to you. Next slide, John. So on the actor side, the message, this is the message received. We receive this new connection request. We log the event just for tracking it. If a connection request isn't already active, we start trying to create the connection. If one is already active, we put it on a backlog queue, continue the processing the request that we're currently processing, and we'll get to this one once we're available. And then the concrete work here, we use the injected connection factory type to attempt to create a connection. If a valid connection is returned without an error, we log that we've created a new connection, and we pass that connection back to the injected connection request through the interface that was given to us by the caller. If the request returns an error, I assume that that means the request was stale, and so I just immediately close the connection. Then I check to see if there are any other pending requests. If so, I go back into this loop to do this again. If not, I just go back to idle waiting. Next slide, John. So what have I done so far? So I've created an API for creating connections. As I've mentioned, the two vectors of change are what type of connection to create and what to do with the connection once it's been created. And these are where the abstractions reflect this. There are a couple other classes here. These classes are concrete. They do concrete work. That concrete work is handling the asynchronous behavior, trying something over and over again, and providing a clean API. These things are not going to change. There's not really a clear vector of change there. So there's no need to create any sort of abstraction around them. Next slide, John. So moving to the next layer, I've got, again, I want a clean API that kind of handles all of this stuff for me. So I obviously need another layer on top of this. What do I do with the connection? Well, I want something that once that connection goes down to retry, so I probably need some more asynchronous behavior. So I create a persistent connection handler actor. And that actor is in charge of persistently handling connections. So when a connection is lost, it sends a message to the factory to retry. And I inject this actor with all the different vectors of change that I have. So the connection factory type, I already mentioned that, is one vector of change. I also, as a user of this API, want a callback to notify me that the connection state has changed. So this is often really useful if you're communicating with a device. In my use cases, I'm communicating with an embedded system, and I have a UI. I want to know on that UI whether or not I'm connected, and I want to be able to immediately respond if I lose or gain the connection. So I want an injectable callback. I want this API that's doing this asynchronous behavior to be able to notify me of what's going on in the background. So that's a vector of change. How I want to be notified, again, that's injected. So these other classes all kind of define these questions here. You know, how do you read from the connection? How do you write to the connection? How do you notify the caller the connection is available? These are all the vectors of change that are injected. Next slide, John. So what does this persistent connection handler look like? On startup, it initializes the connection factory session and then requests a new connection. And the concrete connection request that we've defined here is a message class. Well, it's a child of the connection request that wraps up a message class. So I inject the actor queue into this message class, or not the message class, this child class, and then when a new connection is available, what happens? The factory session sends a message back to the connection handler that this new connection is available. So the connection factory calls into send this message. It doesn't know it's sending a message. It just knows it's adhering to the interface provided by that caller. Next slide, John. So when a new connection is created, this is the method that is called by that message. The persistent connection handler launches a dedicated connection handler that will handle the writing and reading of data from that connection. I also fire off the connection state change callback to notify the caller of the top level API that we now have a valid connection. And I log the event. Next slide, John. This dedicated handler that's launched when a new connection is available provides, it launches a dedicated reader and provides a message to make write requests available when the connection is available. So when you send a request to send a message, this is the method that gets executed. We pass in a write request, and we've injected, when we initialized the API, we injected a concrete write policy, and that write policy kind of defines how the packet is flattened and how it should be written to the connection. And this write request also includes an execution callback, meaning that the caller of the write request wants some confirmation that the write either occurred or didn't occur, or had an error, didn't have an error. Next slide, John. So taking a step back to the very top level API, this is the Initialize, the very high level API that we're going to end up using. This is the constructor method for that persistent connection handler. We launch the actor. I use the same pattern where I send the actor that I've just launched a message to create a reference, so that that reference is now tied to the actor. It's totally safe. It's not going to be shut down by LabVIEW. And then I provide methods for injecting all the vectors of change that a consumer of this API would want. As I said, I've defined that I want the messages in a specific format, which is strings and LabVIEW variants. So I've hard-coded those two vectors of change simply to make it easier to consume the API for an end user. You could make the argument that those should be inputs and should not have been hard-coded there. Again, my use case, it's not a vector of change for me, but all the pieces are here so that if you wanted to build up your own API where you had a different messaging format, it'd be very easy to do. So the two things that a consumer of this API needs to inject are the packet return, which is what to do with a message once it's received, and a connection state callback, what to do when a connection happens. Next slide, John. So sending a message, this API, again, it only provides a couple of methods. One is initialize, one is send a message. So this is our send message method, where you have a string and a variant input that get packaged up into a couple of classes and built up into a write request that gets sent off to the connection manager. And we also inject an execution callback. So this bottom class in yellow is the execution callback. That's injected into the write request. So this method here is synchronous in the fact that if a connection is not available, we're going to know about it right away. We're going to know whether or not the write occurred or didn't occur. And because this queue is protected, the queue isn't available to anyone else. The only way the queue gets exposed is through the API that I have defined. I haven't just launched the actor and let the queue out into the wild. I have guarantees about the behavior of this API. I don't have a timeout on this method because I know, based on the design that I've created, that that method will execute. If the message is sent without an error, I will get a response there. And that's a guarantee that I have because I've encapsulated the API. So one issue with launching an actor and then just giving it to queue out into the wilds for other callers to use is that you can send any actor any message you want, and you can do all sorts of wild things with actors. You can send an actor a message to swap out the actor, where whatever actor was running, you inject your own actor, and now that's the actor that's running on that queue. You can do all sorts of stuff like that, and so by providing just the queue, you haven't really provided any sort of safety or guarantees about the behavior of that actor. Here, I've provided a guarantee of the behavior of the actor because I limit the exposure through the API. So there's one question: was the cost overhead for this abstraction in different operating conditions? The benchmarking that I've done on these layers, it seems like there may be a lot of overhead here, and versus just directly calling it to the TCP IP methods. Obviously, there is overhead. Obviously, it's not going to be as fast as that. My experience has been that it's more than what I would ever need. I think if you're at the point where you need really, really high speed communications, you probably are going to need to design something that's very specifically for that anyways. So this probably wouldn't be an API that you use. But I do have some benchmarks around. I can't remember the benchmarks off my head, but I was pretty impressed and was like, oh, I remember it was definitely less than a millisecond per call to have a message go all the way through. And I think I did some round trips just on my local network on my PC, and a message there and back was, I think, less than a millisecond. So I think for most use cases, for my use case, the overhead is not at all an issue, and the benefits that I get from providing this clean, really easy to use API far outweigh any sort of overhead. Next slide, John. The other thing that I mentioned, the high-level API doesn't expose a read method. And why is that? Because I don't want to have a loop that I just need to continuously pull to check for messages. I want to be notified when a message comes to me. So this, again, is another vector of change. How do you want to be notified that a message is received? So that's an injectable class. And when a connection is created, this dedicated reader is spawned up. It's an actor that just continuously tries to read from the connection. When it gets a valid message, it passes it back through the injected message return, and then just goes back to trying to read again. So this is kind of an implementation of, it's called the Hollywood principle. Don't call us, we'll call you. It calls you when you've received a message. Next slide, John. So kind of putting it all together, this is just a really simple example use case here of calling the API. I don't know if you can really see here, but what I'm doing is initializing the API. This little pop-up test client window here is just a kind of dummy actor that would be a client, an example of a client. The main UI window you see would be your server, and I've created kind of just an example to show messaging through this API, and I've also created two concrete implementations of a message received callback and a connection received or connection made callback, and these are event based, so that if you just kind of showing the example that if you as a consumer of this API, all your loops are driven by events, you could create these very thin classes that hook into this API through user events. So when I receive a message, I don't know if you can read it, but when I receive a message, an event is fired, and it just kind of updates this UI here. So next slide, John. And the test client, just for simplicity, is just a simple actor. In this use case, I just reused the event implementations. A real use case, I would probably create actor message callbacks so that I would get messages to this actor when a message was received or the state change occurred. But just for simplicity, I reused those two event callbacks. Next slide, John. And those callbacks are super simple. They're really two methods, right? Construct, which creates the user event, and then the return data packet for the message received. And the connection callback is basically the same. It's got a construct, which creates the event, and then executes the state change callback. So these are super simple classes. A consumer of this API, even if they're not very familiar with object-oriented programming, could probably figure out how to create these classes and use them in a way that matches their paradigm. And we can see that the implementation here is actually super simple. Next slide, John. So these thin classes, like I said, allow us to use the API the way we want. And here at the end, so we've got a total of 6 actors, 5 are concrete, and 1 is an abstract parent. I have absolutely no abstract messages. There's no requirement on the user to know about these actors or to use them. And I kind of want to make this point that most of the applications I write have a lot of actors, sometimes hundreds of them, but often they don't need to directly interact through queues. It's often better to have them interact through a clean, clear API. No need for abstract messages. Any type of abstraction is injected into the actor, and the actor's queue is protected around this other class to kind of guarantee the behaviors of that actor. Next slide, John. And so kind of wrapping it all up, some final thoughts. When writing code, ask yourself if these modules, I'll get back to that question in a second. If these interactive modules should know about each other, ask yourself if your application dependencies on non-specific application modules can be reduced through interfaces. When writing APIs, identify the vectors of change. Ask yourself if you can create an abstraction around those vectors of change to make the use of that API a little bit easier. And that's pretty much it. So it looks like I got a couple questions. Is it possible to have the example file to read the code? The network messenger is publicly available. It's open source software. I will, at some point in this summit, I will put up the link to that so that it's, yeah, Stephen, all code in this presentation is open source. So if you go to the Compose Systems Bitbucket, you can probably find it right now. It should be, I think, Compose Networking or Compose Messenger. There you go, Compose Network Interface. So yeah, the code is publicly available. Another question, you have no checking of types classes, only at runtime. So a couple questions. I'm not sure about the checking of types classes only at runtime. So the types classes are injected at runtime. There's no type checking of concrete classes in the code. It's purely dependency injection, where you're injecting your concrete callbacks, if that's the question. Brian's question: how is debugging for users when they send message to hidden actors and don't receive a return message? So yes, there is a complete log of everything that's happened here, and that log is something that gets injected. So if you don't inject a log into this, it all works just fine. You don't need to inject a log. It's there for debug. Yeah, going back to this example, that blue wire at the top is an event. Again, this is another piece of open source software that's publicly available, our event logging package that it's very useful. It's used pretty much in all of our modules. It's injected throughout, and that makes debugging all this stuff pretty easy. Question on circular dependencies. Circular dependencies are bad. You can resolve them through interfaces. Looks like we should break, so I think I'm going to end here and maybe hop into one of the other sessions, to answer other questions if anyone else has any ones. So thank you for everyone for attending and asking questions. This was fun. So thanks, and I will see all the other presenters at their presentations.